the total area is given by, for the curve A1, we will take the modulus A1 to make it positive. First, I will calculate the first half of the region so that I will get the second half of the region same. The limits are given for y. So, therefore, we have to take the integral of the form g of y dx. Remember, when you have dy here, functions has to be expressed in terms of y. If you have dx here, functions are expected in terms of x here. Hello everyone, a warm welcome to one and all. This is your Shruti ma'am lecturing in Vidhyaashram, the Temple of Excellence, Mysuru. So here we are in the new chapter, Applications of Integrals. So in our previous sessions, we have studied about the indefinite integrals as well as definite integrals. So definite integrals are applicable to find the area under the curves. So in today's session, we are going to find out the area under the curves as well as the area bounded by the region between a curve and a line. So let's study how definite integrals helps us to find out area under the curve. So here are few examples taken in general. So the very first case here, you can see the area above the x-axis, and since this is in the first quadrant, clearly the area is positive, that is f of x is greater than 0. So here y is equal to f of x is some curve. So how we are going to calculate the area of the complete curve here under the curve y is equal to f of x and the coordinates x is equal to a, x is equal to b above the x-axis. So what we will do here, we will take a very small rectangles where the curve is almost equal to a straight line, and there we will draw a rectangle. So we know that area of a rectangle is length into breadth. So therefore the area of this part becomes y into dx. So similarly, we will divide the curve into small rectangles where the curve is almost equal to a straight line, and there we will calculate the area of each rectangle from interval a to b, and we will total it. Then we will get the total area of the curve. So here, by the definition of the definite integrals, so the area of the region bounded by the curve y is equal to f of x along the x-axis and the lines x is equal to a, x is equal to b. That is, we can call it as an interval from a to b, and it is given by area is equal to integral f of x dx. So here it must be from a to b here. Next we have one more type of curve you can see here. So here the area is bounded by the curve x is equal to g of y. Why it is x is equal to g of y? The function is expressed in terms of x as a dependent variable and y as an independent variable. And here also what we will do is, we will take a very tiny rectangles, very small rectangles, so that this curve is almost equal to a straight line, and there we will draw a rectangle. We will find the area of rectangle. Like that, we will divide the curve by small rectangles and then we will total it. So integration is nothing but total. So therefore, we will find the area of each rectangles and we will find the total area of the bounded region there. So therefore, here the area goes from C to D. So that is from the lower ordinates to the upper ordinates. So from C to D, g of y dy, because here we are calculating the area along y-axis. So when it is along the y-axis, the function changes to g of y dy. That means all the variables are expressed in terms of y here, and we will integrate it. So next, suppose whenever the curve is below the x-axis, what happens? Even though function is negative, that is, even though f of x is negative, we will take always the absolute value, that is the modulus value of an area, because area is always positive. So therefore, for the curve below y is equal to f of x and between x is equal to a, x is equal to b, it is integral from a to b f of x dx. If it lies below the curve, the value will become negative. We will take the modulus so that it becomes positive, because area is always a positive quantity. So this is how we will calculate the area below x-axis. Next, we arrive at some curve where it goes both in positive x-axis and negative x-axis. Then how we will calculate those area? So here is an example we have taken, and here is an interval from x is equal to a to x is equal to b. So from here to here, how we will calculate? So let A1 be the area below the x-axis and A2 be the area above the x-axis. Above the x-axis, f of x is positive. So we will get the total area, that is integral from a to b f of x dx, and below the area you have to take only the absolute values. So therefore the total area is given by, for the curve A1 we will take the modulus A1 to make it positive, and for curve A2 it is A2 only. So this is how we will sum up the areas when it is below the x-axis and above the x-axis. Whenever the curve is below the x-axis, we will take the modulus of the integral value of f of x dx from the limits a to b. Now let's take problems related to calculation of area under the curve. So here is our first question. Find the area enclosed by the parabola y square is equal to 4ax and its latest rectum by the method of integration. So here we know that the distance from the origin to the focus is always a, 0, and this distance we usually call it as a. So therefore here x varies from 0 to a because the curve ends at the latest rectum whose distance is at a. So therefore our lower limit is 0, 0, 0, so 0, and upper limit is a. So therefore here area. So what I will do here, I'll calculate only the positive side of the x-axis. We know that parabola is a symmetric. Symmetric means it is exactly mirror image towards x-axis here. If I calculate first half, then if I double it, then I will get the total area. Since if you calculate this area, this is same as the area below the curve. If you if you double it, you will get the total area of the parabola. So therefore what I will do, I will take 2 times f of x dx, and integral goes from 0 to a because we have the limits from 0 to a. So what is f of x? F of x is y square here. So we need y square is equal to 4ax. So therefore what happens to y? Y becomes 2 root a into root x. So here f of x is nothing but 2 times 0 to a y into dx. So therefore here it becomes 2 times integral from 0 to a. What is y we have? 2 root a into root x into dx. We can take 2 root a outside because it is a constant. So therefore this becomes 2 into 2 root a integral from 0 to a root x dx. So root x index power is x to the power half. We know that integral of x power n is x power n plus 1 by n plus 1. So therefore this becomes 4 root a. Integral from 0 to a becomes x to the power 3 by 2 by 3 by 2, and limits are 0 and a. So we have 4 root a. We will take up 3 by 2 outside, then it becomes 2 by 3, and here we'll apply the limit a to the power 3 by 2 minus 0. So here you have 8 by 3. Root a is nothing but a to the power half. A to the power half, a to the power 3 by 2. So half plus 3 by 2 becomes 4 by 2. So therefore it becomes a square. So we will write the units in the form of square units. So therefore the area bounded by the parabola with its latest rectum is 8 by 3 a square units. So here if you have given the value of a, suppose if x is equal to 2, suppose if x is equal to 3, then the total area becomes 8 by 3 times a square, that is 8 by 3 times 4 square, 8 by 3 times 2 square. So in general the total area of the parabola bounded by its latest rectum is given by 8 by 3 a square units. So next question, find the area of the region bounded by the curve y square is equal to 4x, y axis, and the line x is equal to 3. So we need to calculate the area bounded by this parabola as well as its lattice rectum. So lattice rectum is given, that is x is equal to 3 here, and the equation of the parabola is y square is equal to 4x. What is the area we will calculate? Area is equal to integral from a to b. What is the lower limit here? It is 0. What is the upper limit? It is 3 for x. So this is the coordinate of x and y, and here it is we have 3, 0. So therefore the coordinates of x varies from 0 to 3. What is our f of x here? F of x is y square, but f of x must be equal to y. So therefore here y into dx. Again, what I have applied here, first I will calculate the first half of the region so that I will get the second half of the region same. So I will double it. So therefore it is 2 times 0 to 3 y into dx. So what is y here? Y is again 4x, that will it becomes 2 root x. So therefore it is 2 into 0 to 3 2 root x dx. Take 2 outside, it becomes 4. So apply the integral 0 to 3 root x dx. So what happens here? It is 4 into root x become x to the power 3 by 2 by 3 by 2, 0 to 3. So when you multiply here, it becomes 8 by 3 times. Apply the upper as well as lower limit. It is 3 to the power 3 by 2 minus 0. So therefore here it becomes 8 by 3. So 3 cube is 27. So square root of 27, we can write it as 27 as 9 threes are. So therefore it is 3 root 3. So 3 get cancelled. So therefore the answer is 8 root 3 square units. So this is the area bounded by the region, that is x is equal to 3 as well as y square is equal to 4x. Find the area of the region bounded by the curve y is equal to x square and the line y is equal to 4 and the y-axis in the first quadrant. Here the limits are given for y. So therefore we have to take the integral of the form g of y dx. So therefore here what happens? So therefore area is, so what are the limits? So from 0 to 4 for y. So that is from 0 to y, x into dy we have to take, x into dy. So therefore what is x here? We have y is equal to x square. So therefore x square is equal to y. This implies x is equal to root y. Only take the positive quantities for the root because area is positive. So what happens here? 0 to 4 root y dy. Why I have not written 2 times here? Because they have asked you only to calculate the area in the first quadrant. If they have asked you to find the area of the parabola bounded by the line y is equal to 4, then you have to include complete area. But since they have strictly asked you, you have to find the only area in the first quadrant. So therefore the region lies from 0 to 4 and it is that y into dx form. So therefore here I have taken x into dy because the limits are for y. So whenever the limits of y, it is for y limits x into dy. If it is for x limits, then it is y into dx. Now no need to write 2 here. So therefore what happens here? Root y is again y to the power 3 by 2 divided by 3 by 2. Apply the limits from 0 to 4. Take 3 by 2 outside, then it becomes 2 by 3. If you apply the limit, it is 4 to the power 3 by 2 minus 0. So 4 cube is 64 and square root of 64 is 8. So 2 by 3 into 8, which is 16 by 3 square units. So this is the total area of this curve. Next, find the area of the region bounded by the curve y square is equal to 4x, y-axis and the line y is equal to 3. So now here the limits are given in terms of y. So therefore what is the limit? Y is equal to 3 and it varies from 0 to 3. So therefore the limits are from 0 to 3. So area. So again we have to take the area bounded by the y-axis and the line y is equal to 3. So this is the line y is equal to 3 and this is the area covered by the y-axis and from 0 to 3. So the shaded portion is the bounded region, that is the area required. So therefore area is from 0 to 3. Now we have to take x into dy. But what is x here? We have y square is equal to 4x. So therefore what happens for x? X is y square divided by 4. So let us substitute here. So it becomes 0 to 3 y square by 4 into dy. Take 1 by 4 outside the integral. Apply integration for y square into dy. So if you apply y square into dy, it is 1 by 4 y cube divided by 3 from 0 to 3. So take 3 outside, then it becomes 1 by 12. Apply the integral for y cube. It is 3 cube minus 0. 3 cube minus 0, which is 27 by 12. Again dividing 9 divided by 4 square units. So this is the area bounded by the region. So y square is equal to 4x and the line y is equal to 3. Next one, find the area of the region bounded by the curve y square is equal to 9x and the line x is equal to 2, x is equal to 4 and the x-axis in the first quadrant. So here is the curve taken. I have taken x and y-axis, have drawn a curve y square is equal to 9x. So this is only a rough diagram. So I have drawn a curve y square is equal to 9x, which is a parabola. I have taken a line x is equal to 2 and x is equal to 4. We need to calculate the area above the x-axis only in the first quadrant. So what is this? This shaded region is the required region or required area, that is between the curve y square is equal to 9x and between the lines x is equal to 2, x is equal to 4 and in the first quadrant. So therefore, here we have the limits for x. So that is 2 to 4 and the required area is equal to. So since we have to express in terms of y, so therefore it is y into dx. So we have y square is equal to 9x here. What is y? Y is equal to 3 root x. So 3 root x. So therefore here integral from 2 to 4, 3 root x dx and 3 outside. So root x becomes x to the power 3 by 2 by 3 by 2. Apply the limit 2 to 4. So take 3 outside here, then it becomes 3 into 2 by 3. If you apply the limits, it is 4 to the power 3 by 2 minus 2 to the power 3 by 2. So 3 get cancels 2. So 4 cube is 64. 64 square root is 8. Next here you have 2 cube is 8. Square root of 8 is 2 root 2. So when you multiply it, 16 minus 4 root 2 square units. So this is the area of the required region. Next, find the area lying between the curve y square is equal to 4x and y is equal to 2x. So roughly I have taken a diagram, y square is equal to 4x and the line y is equal to 2x. So clearly they have not mentioned the limits here. So since it both meet its origin, the first limit is 0. What about the second limit? So here I have taken a marked as 1, 2. So this curve and the line touches at 0, 0 and 1, 2. How? We have here y square is equal to 4x and we have y is equal to 2x. So put y is equal to 2x here. What happens? 2x whole square is equal to 4x. So 4x square is equal to 4x. So 4x cancels, we will get x is equal to 1. And from this, if you put x is equal to 0, y is also 0. So this is also possible. So therefore the limits are x is equal to 0. What happens if you put x is equal to 1? If you put x is equal to 1, then y is equal to 2. So therefore, the curve meet at 0, 0 and 1, 2. So this is what you have to write in your examination to know the limits. So now let's calculate the area. So how to calculate the area? So here you can see here, we have to find the area between these regions. That means, so the total area of the parabola has to be subtracted from the area covered by this. So therefore, the total complete area, if it is subtracted from this area, then you will get the shaded region. So that is why we will take area is equal to integral of, what is the limit? 0 to 1. So first function we have 4x. So that is, we will take it in the form of f of x minus g of x into dx. So let me take f of x as this function and g of x as this function. So if you subtract the total area from this shaded region, you will get the blue shaded region. So that is why, so f of x is actually y square is given. So if y square is equal to 4x, so I should take y is equal to 2 root x, and the second is already expressed in terms of y. So let me take this as 0 to 1, 2 root x minus 2x dx. So we can take 2 outside. It becomes 0 to 1 root x minus x dx. So 2 times apply the integral. So this becomes x to the power 3 by 2 by 3 by 2 and minus x square by 2. 0 to 1. So now 2 times, so here we have 1. So if you apply the limit 1, then it becomes 2 by 3. And if you apply the limit 1 here, it becomes 1 by 2. So minus, for 0 it is 0 minus 0. So therefore it becomes 4 by 3 minus 2 minus 1 by 2 becomes here 1. So which becomes 1 by 3 square units. So this is the area bounded by the region. Next is, find the area of the region bounded by x square is equal to 4y, y is equal to 2, y is equal to 4 and the y-axis in the first quadrant. So all the variables are expressed in terms of y. We have the limits for y, we have functions with respect to y here. So therefore we can find the area, and clearly they have mentioned the area must be in first quadrant. So therefore here we have a curve x square is equal to 4y. X square is equal to 4y is an upper parabola. So therefore it is like this. We have a straight line y is equal to 2, y is equal to 4, and in the y-axis the shaded region represents the required area. So therefore now we have area integral from 2 to 4 x into dy. So what is x we have to take? We have x square is equal to 4y. So what is x? It is 2 root y. So therefore this becomes integral from 2 to 4, 2 root y dy. Remember, when you have dy here, functions has to be expressed in terms of y. If you have dx here, functions are expected in terms of x here. So whenever the limits are given in terms of y, it is x into dy. Whenever the limits are given in terms of x, it is y into dx. So now let's take 2 outside the function. Root y becomes y to the power 3 by 2 divided by 3 by 2, and apply the limits from 2 to 4. We can also take 3 by 2 outside the function. Then it becomes 4 by 3. Let us apply the limit now. So y to the power 3 by 2 is 4 to the power 3 by 2 minus 2 to the power 3 by 2. So we have 4 by 3. When you solve 4 cube 64, 64 square root of 64 is 8, and 8 square root of 8 is 2 root 2. So you can take 2 as a common factor again here. Then if you take 2 outside, it is 4 to the 8 by 3, 4 minus root 2 square units. So this is the required area. Next, Find the area bounded by the curve y is equal to sin x between x is equal to 0 and x is equal to 2 pi. So we know that the curve lies both in first quadrant, that is in the upper side of the x-axis as well as below the x-axis. And above the x-axis the function is positive, so we can calculate the area. But below the x-axis the function is negative. We have to apply the modulus for the required area, and the limits can be splitted to 0 to pi and pi to 2 pi. So why? Because we have learned the properties of definite integrals, that is whenever you have a integral from a to b, you can split the limits from a to c to c to b, where c belongs to the interval a comma b. Since here pi belongs to the interval 0 comma 2 pi, so we can split this interval to 0 to pi 2 pi, which is one and the same. So let me take here the total area is equal to the first one. So this is the origin, from 0 to pi we are calculating. So therefore it is 0 to pi. The function is given as sin x. So sin x dx plus, and here it is pi to 2 pi. Again the function given is sin x dx. Here we have to take the modulus of this function because below x-axis the curve lies. We have to make the area positive. So now here, what is integral of sine? Minus cos. Minus cos x. Apply the limit from 0 to pi. Next here again, modulus. So let us write integral of sine is minus cos x pi to 2 pi. Take the modulus here. So now here we have minus. Write minus outside. Apply the limit. Cos pi minus cos 0. Again here, take minus outside. Apply the limit. Cos 2 pi minus cos pi. We know that cos 0 is minus 1. So cos 2 pi, cos 4 pi, that is cos of even pi will become 1. And cos odd pi is minus 1. So therefore here it is minus of minus 1 plus modulus. Since you have modulus, if you have negative also it becomes positive. So here minus, out here we have minus 1 again modulus. Next minus 1 is minus 2. Minus 2 outside minus, it becomes plus 2. Next we have minus 1 minus 2. Outside minus plus 2. Modulus, it becomes plus 2. So therefore the answer is 4 square units. So this is the area bounded by the curve sin x from 0 to 2 pi. So this is the total required area bounded by the curve y is equal to sin x. Similarly, we can find the area bounded by any trigonometric curves under the given integrals. So in today's session, we have learned how to calculate area using definite integral whenever it is bounded by any curve and the straight line. So we'll meet you in the next session calculating the area of integrals. Until then, keep watching, keep learning, keep exploring. Thank you.